Good afternoon, everybody. I'm Mike Bursell. I'm the Executive Director of the Confidential Computing Consortium, and I am not a lawyer. Okay, so please don't consider any of this legal and contact your organization if you care about these things, and everyone will be nice and happy. Arigato gozaimasu. So first of all, let's discuss exactly what we mean by digital sovereignty. And it is sovereignty, not sovereignty. I'm a bit of a pedant about language. I apologize, but there we go. So here's one description from the World Economic Forum, which is control over our own digital destiny, the data, the hardware, the software that you rely on and create. And basically what you're aiming to do is to remove the ability of foreign-owned or controlled organizations or government to access data which is owned by, is about, or important to national citizens or interests. And I think that or governments is important here. And also you want to have to remove dependence on foreign-owned or controlled infrastructure. So what does all this mean? What it means is that when you have important data which is being created or managed either by the government or by organizations about your citizens or about their affairs, then you don't want foreign companies to be able to mess with it, and you don't want foreign governments to be able to control or change or remove access to it if it is critical to your citizens, to your businesses, or to your government. But I think we also need to be pragmatic and realize that this is about reducing this capability. There are always going to be ways in which foreign governments and organizations may, through fair means or foul, i.e. by doing bad things or okay things, to actually affect these things. So we're always taking pragmatic decisions here. So there are, I think, three main areas. There is control of data. There's control of the technology that allows data to be managed. And there's operational independence, which is actually being able to make this keep running and availability and all the things that you expect. So in terms of data control, some of the concerns are that, well, an organization might leak information or change information. And a government might force disclosure or change of information. So let's say you have tax information about your citizens. You do not want a foreign organization being able to see that data or leak that data. Equally, you don't want a government, a foreign government, to serve a court order on another organization, like a cloud provider, and say, we want to see this data. So it may be considered legitimate by, let's say, the UK government to request information about a Japanese citizen. Well, the Japanese government may disagree with that. And so data control is about stopping that happening in ways which are not controlled. Oh, and this includes, applications and AI models as well. We should be aware that this can be quite complex. So in terms of technological control, this is about control over the infrastructure, that's hardware and software, the supply chain, control plane, all those sorts of things. We heard the previous speaker talking about supply chain and control over that. It's quite a complex set of things we need to worry about. And in terms of operational independence, yes, it's control of actually running this, making sure its availability, and also being able to say that I can apply my local rules to this rather than a foreign government's regulations and rules. It's my data, my citizens, my operations. I should be in charge of that. And all these three areas are things which are very important to folks at the moment. But I think we also need to be aware that we need to be pragmatic. We need to realize that we operate in the real world. And so sometimes keeping everything, all your operations in your borders, in data centers which sit within your country, may be difficult or impossible. Sometimes the appropriate infrastructure isn't available. For instance, I was speaking to a member of the CCC yesterday who was saying that actually availability of some of the new GPUs has not had all of the requirements turned on to give them what they require. Also, sometimes you may just, if you're operating a business, you care about failover and disaster recovery and all those sorts of things. So my first earthquake 2 days ago, and Japan is very aware of managing infrastructure, and sometimes it may be felt appropriate to have failover in a different country to manage these sorts of issues. And thirdly, of course, many businesses have multinational operations, and saying to them, you can only do these things in these places, may be very, very difficult for them to manage. So, this means that sometimes home country only operations are impossible or so constricting on the operations of your businesses that actually it's going to be a bad thing. So what I want to talk about from here on is what happens if you decide you do need to have cross-jurisdictional operations, i.e. to have some of your operations, some of your data in places which are not directly within your home country. So these are kind of the three sets of things. Those are the three operations types that I listed. We've got rules and regulations, data applications and operations, and they're all interconnected. Of course they are. But I would suggest that the things you tend to care about for each of these are these. So for data and applications, you want confidentiality and you want integrity, i.e. you want to be able to keep things hidden where appropriate and also to be sure that they're not changed. Sometimes you want one, sometimes you want the other. Oftentimes you want both of those capabilities available. In terms of operations, one of the key things is availability. Will it be available? Will it keep running when I need it for the things I need? Again, the previous speaker was talking about election day and how availability can be a particular struggle on election day. And I kind of think of rules and regulations typically as non-technical controls at the top. What I want to concentrate on for the rest of this talk really is the data on the operations and the confidentiality and integrity. So that's where we're going to go from now. So the next thing is, in the title of the talk, it said PETs, P-E-Ts, as a solution to digital or data sovereignty. What are privacy-enhancing technologies? Does everybody here know what a privacy-enhancing technology is? Hands up. Not everybody, that's fine. I know you do, Kudo-san. Yes, thank you. And I'm relieved that you do as well, Hart. That would be concerning if not. So there are many and sometimes conflicting definitions of what a PET is. Here's one that I quite like. It's a technology to protect and or restrict unauthorized use of private data. And there's important words here. It's protect and or restrict and private data. Okay, so it's data we're talking about mainly here, and it's about protecting and restricting. But of course, that is the important word here. It's unauthorized. We do want people who have authorized authority to access it. And there's an important focus here on data in use. So we have, I hope, all been encrypting our data in transport, so on the network, and also at rest, so when it's in storage on databases or file systems. What PETs are interested in is about protecting, restricting access to data while it is actually being used by an application typically in RAM, which is very different to how we tend to think of data at rest or on the network. So there are a variety of techniques: isolation, encryption, anonymization, pseudonymization. All of them focus here on preserving the confidentiality of that data. And here is a fairly representative list of some of the key ones, and don't you worry, heart, FHE is up there, of course it is. And here's a picture of what I think we're trying to achieve. So on the left, you have an organization, a government, whatever it is, which is trying to access sensitive data in a sensitive application. And the big white box is a computer. That's how I think of computers, okay? And it's got a host operating system at the bottom, and it's got a chip at the bottom as well. And the box is maybe a container, maybe a VM, but it's RAM, basically. And so this is where we want to be. And of course, the green arrow means that it's nice and secure and it's nice and safe. And when we have and we want to block any bad people getting to it, right? And in our home territory, maybe we can do that. But if we have a machine which is in foreign territory, it's very difficult to stop someone from a foreign government being given access to that data. And given that we can't necessarily control access to that data, that means we can't even be sure that the link, the transport, is also secure, because if they can see in that data, they can see any keys, cryptographic keys, which means that we can't even be sure that what we're getting has integrity or has got confidentiality. So, and of course, we also have the problem that not just foreign governments, but maybe the hyperscaler, the CSP can look in, maybe a hacker can look in as well. And this is what we're trying to avoid. And the promise of PETs, PETs, is that you use the technology somehow to isolate or protect that app and that data whilst it's in use. And if you're doing it right, none of those actors will have access to it. We also want to be in a position where we can actually ensure the integrity of that key so that we can have a nice TLS or similar connection back to the home organization or government. So that is where we're trying to get. Let's talk a little bit about some of the capabilities of the different PETs. So I've listed 5 of the kind of key ones on the left, with some of the different capabilities they have. So the first one is that all of them provide confidentiality of data. So homomorphic encryption is a very clever mathematical technique where you can do certain operations on data which is always encrypted, basically in memory. So at no point is it is decrypted. It just sits there and you do operations on it and you get information out. You can't do general computation with homomorphic encryption, but there are many very clever things you can do, and the maths is great. Unfortunately, it's very slow as well. Fully homomorphic encryption can be millions of times slower than standard native. But it is very secure and the maths is fantastic. Federated learning is a technique where you split information up into different parts and you can operate on those different parts in such a way that you can prove that none of the different parties have access to all of that data. Again, confidentiality is there. Synthetic data, is a technique by which if you're operating on data sets and you're worried that the data set may leak, you can create data which basically gives you the same sort of outputs. But it's, again, only useful for very specific use cases. And secure multi-party compute is similar in other ways to the federated learning. And I'm not an expert, I have to admit, in that. Confidential computing is different. So confidential computing, first of all, is not a software-based capability. It is a hardware-based capability. There are chips from Intel and AMD and NVIDIA, all of which provide confidential computing. IBM has has hardware which does it as well, I believe. And what they do is provide capabilities at chip level. So chip level instructions which isolate the data, basically encrypt the data in memory. So at no point is it decrypted except on the chip itself. And that means that even if you have access to that machine, you shouldn't be able to look inside the RAM and be able to get any of the information out. So good things about this, it not only provides confidentiality, it provides integrity checking as well. And you can just write a standard application, depending on how you set it up, and run that in the standard way. It's also very performant. It's maybe a few % slower, again, depending on your use case, than standard computing. So all of them, yes, provide confidentiality, and confidential computing provides the other pieces as well. So what that is doing is we're now looking at providing confidentiality and the integrity. One of the issues we have is that availability is something that we really can't guarantee. There are basically no assurances when somebody else has control over the operations of a machine. Even if you can provide confidentiality and integrity, then they can always just stop resources being assigned, whether it's network resources or RAM or just kernel cycles, processor cycles to your application, and thereby stop you being able to have the availability. So there's not much we can do about that other than monitoring and observing. And of course, monitoring and observing applications which are confidential could be very complex in and of itself, but that's a conversation for another day. So I want to point out that none of these provides availability assurances, but also that no technology, security technology, is perfect. Now, the mathematics of some of the software-based ones are absolutely fantastic. And that is an area where we are pretty sure, I think, that we have very good assurances around the security. But to come on to hardware-based controls, they are absolutely much faster than other approaches, and they provide for general computation and the integrity assurances, but they are not perfect. And the if you look at the assurances that the manufacturers provide around confidential computing, they generally all exclude physical attacks on the chip itself. And there have been some attacks on chips, including some side channel attacks, which have been shown to breach some of the confidentiality capabilities of confidential computing. So I want to leave some time for questions. So I'm going to go to a summary now. So software-based capabilities provide you with strong mathematical assurances, but all of them have performance and implementation problems, in that you can't just take an existing application and use one of the software-based PETs. Hardware-based capabilities provide that ease of implementation and close to native performance, but there are situations in which they may be subject to physical attacks. But you can combine these technologies, and the important thing to be doing here is to understand the risks and design, as you always should do, of course, for defense in depth. And it may be that different parts of a system, in fact, need different controls. And again, I'm happy to delve into this in more detail if people would like, but the attacks on confidential computing are such that they need to be pretty sophisticated, and combining them in a way that allows a foreign government, for instance, or a foreign actor to have a definable impact against your data is a risk that is probably quantifiable, something that you can certainly work on. And like most cybersecurity and business decisions, these technologies allow you to make different risk decisions. Where is the attack most likely to happen? Would applying some of these technologies allow you to put some or all of your capabilities in jurisdictions which you do not directly control? Is the balance of being able to keep availability, to scale fast, to have access to the latest technologies, is that good enough with these technologies? And I think in many cases it can be, to allow this sort of use. So for instance, to say, if we're using this technology, it's okay to do GDPR-based work outside of the EU area. Is that acceptable? And I think that we are seeing use cases where that absolutely is considered by the regulators to be acceptable use. So before I finish, I just want to talk very briefly about the Confidential Computing Consortium, because we are part of the Linux Foundation, and our job is to work on open source projects which provide confidential computing, and also to accelerate the adoption of confidential computing through open collaboration. We have 50 or 60 members approximately from very large, Intel, AMD, Huawei, Meta, Azure, TikTok, down to 1 or 2 people startups. Also, we have a number of academic members, including IISec, based here in Tokyo. We also have a 3 months free membership for startups. If you're under 100 people, you get to have free 12 months of membership. So that is a very bad picture of me, which I tried to make anime-like. You can find me there on LinkedIn, and you can find more about the Confidential Computing Consortium at confidentialcomputing.io. So thank you very much indeed. As I said, I wanted to leave time for questions. I think we've got a fair amount of time. So are there any questions? At the back, sir.
You mentioned physical attacks. Has anybody done research in terms of the legal capabilities or the legal frameworks in different jurisdictions about what a company can be compelled to do? For example, which countries can compel a ISP to physically attack the confidential computing hardware?
Sure. So there's a question there about physical attacks, and specifically what governments can force, for instance, ISVs or CSPs to do in terms of attacking and getting influence. I'm not aware of any particular studies. I think generally the law in most situations is they can force companies to take reasonable steps, but I don't know what those reasonable steps would look like. So, for instance, in terms of the confidential computing attacks, the most recent ones that are known about involve taking the chip out, putting custom-made silicon between the chip and the chip housing, and then doing some fairly sophisticated work there. And you need to do that on a chip-by-chip basis, on a system-by-system basis, which would be very difficult to do, but not impossible. And I think that's what it comes down to. To what extent is that likely? You'd also need to be ensuring that the workloads were in the places you thought they were, and having access to all of these things. And so I think jurisdictionally, is it possible? Probably. Operationally, is it plausible? I think that's a very much more tricky question. Usama has a question. That's always a worry.
I have a bunch of questions, but I will start with one and give it the opportunity of others.
Thank you, Usama.
So you mentioned about CSP being out of the TCB. Of course, I will, as a researcher, disagree with that. I think there is no CSP which claims to be out of the CSP, out of the TCB, Trusted Computing Base itself.
I don't think I did say that, actually, but I
think you had a slide where CSP, if you go back on one of the slides, CSP and hyperscaler was shown as a cross.
What I said is we're trying to stop this happening. We're trying to stop them having access to the sensitive app and the data. There are some complexities in terms of things like UEFI I'm very aware of, which make some of this difficult. But again, this is not just confidential computing. If, for instance, you're doing FHE, I think they probably would be outside the TCB in this context.
I don't see any problem in FHE because you have the encrypted data sent to the CSP. So CSP actually cannot do anything in case of FHE. Yes. It's only encrypted data. The key remains with you, and all it can do is just maybe change some values, and then you don't trust the results. And by same reason, I don't see why you had a cross in FHE for data integrity. If something was changed, you cannot decrypt it, and you basically discard that data output that comes out. So
let's not have this detailed conversation about differences. I could have done it either way. It's not a property which is directly designed into FHE, although I do take your point about likely being able to see it. So I'm trying not to give too technical a description here. So let's move on to sort of others. I'm very happy to have these discussions. These are the sorts of discussions we absolutely have in the Confidential Computer Consortium, which people are very welcome to join. You do not need to be a member to come along to our meetings. So please do.
Yeah, sure. My point was just that the table, I found it to be unfair. Like there are a number of subtleties, and it's too biased towards
confidential computing. No, that's fair enough. Maybe there should be a green tick against integrity there, for instance. Fair enough.
Yeah.
Okay. Thank you. Any other questions or comments? Yes, in the orange beanie, very fetching.
Want to make sure you saw me. So when it comes to confidential computing, is this more on the side of service owners that are having control of this? It's the first time I've heard of it. So I was wondering, like, as a user, is this a mechanism for individuals to control their data, or is this something at the like a service owner level?
Sure. So basically, the way confidential computing works is very, very simplistic. And some will bring me up on this, but I'm going to keep it very simple. Is certain chips have this capability. It's CPUs and GPUs. And what you can do is to say to the chip via the OS, please set up what's called a trusted execution environment. It's basically an area of memory protected by a key. What I can then do is put my application and my data into that trusted execution environment, that TEE, and using something called remote attestation, have cryptographic assurances that it is set up correctly and it is what I think should be in there. So that as long as that capability is offered by a CSP, then you as a user can absolutely use it. You can get as long as you're willing to pay the money for the chips and the chassis and set it up, you could absolutely run that at home as well. It's server-based high-level chips generally, although, for instance, Fujitsu or Monaka chip is coming soon, and that is ARM-based. So I think we're going to be seeing more ARM-based, maybe smaller ones, and there's some work on RISC-V approaches as well. So there's a number of things, but mostly server-based, but there's nothing to stop an individual user using it. And in fact, there are a number of Web3-based approaches, which is trying to democratize and decentralize use of that technology as well. No problem. One over here, thank you.
So I'm not that familiar with confidential computing, but I see there's a software and hardware difference. So I'm wondering, like, what is the difference between the trust model of confidential computing and, say, homomorphic encryption? Because as for my understanding, if you're using homomorphic encryption and you do not care about integrity as such, then the only thing you trust with the software should be the software itself. But with the confidential computing, it seems you also have to trust the Intel or AMD or ARM that is making the hardware.
Absolutely, you do. So the trust model is quite different. There's a number of things you need to trust in the confidential computing model. So the first one is the chip itself, and therefore the manufacturer of that chip. The next is, to Osama's point specifically, if you're using a standard VM from a CSP, most of them will put their own UEFI in it, in the VM, which means that actually you need to trust them to some degree. Now, if those are open source, which is beginning to happen, then actually you can have a check of them and be fairly happy with them. So that's getting better. Beyond that, the final thing you need to trust is the attestation verification service. So that is, I talked about being able to get basically a cryptographic quote measurement of what is in there, which is based on a key within the chip. And so that needs to go basically off machine, and someone you trust needs to check against known good values that the T is set up correctly, it's on a chip which you believe is a real one, and that what is in there is what you think they are. So there are 2/3 things you should need to trust, apart from your own code. One is the chip and its supply chain. 2 is the attestation verification service, and 3 is anything that goes into that VM, if you're using a VM that you didn't put there yourself, which is typically these days UEFI. There are absolutely approaches which do not use UEFI and create their own, for instance, little mini OS based, for instance, on WebAssembly, which don't require the UEFI, and therefore you're removing that particular concern about the CSP provided software, firmware, out of it. So those are the things you need to trust. When I say the chip, that also includes the microcode provided by the chip manufacturer, but that's all part of the attestation check that you're doing.
Thank you.
That's right. Happy to go into more detail if you want, but maybe later on. Any other questions? Okay, come on then, Simon.
So since there are no more, so I will come to my nasty questions. First, I want to quickly...
Oh, we're out of time. Oh, no, we're not. Okay.
So I just want to quickly tell you the last question. I have a talk in the Confidential Computing Microconference, if you are attending that on Thursday. There I will talk about attested TLS, which is about how these guarantees work and how we are standardizing it in the IETF. And on Friday, I'm talking in the security microconference about some of the security issues that are there in attestation and TLS and so on. Coming back to the questions part, specifically for integrity for confidential computing, I think that's still a bit, that hurts me a little bit because of the fact that the attested TLS protocols that currently exist still do not provide you any guarantee at all that which CSP we are talking about.
Okay, so to be very specific, you're talking about TLS specifically there. That is, TLS is not a property of confidential computing. Yes, it's built on top, but are you questioning the property of integrity for any of the implementations or of confidential computing, or only of things built on top of them?
So nothing about standard TLS. Standard TLS.
No, I wasn't talking about TLS.
Attested TLS.
Yeah, but I'm not talking about. Sorry, Osam. I'm not talking about TLS here, right? I'm talking about confidential computing. So I agree that when we start building things on top, we need to be very careful about them. But the claims I'm making were not related to TLS. To be clear.
But I would argue that attested TLS, or let's say attestation, is a fundamental property also by the definition of confidential computing. So we had a lot of back and forth.
Okay, I'm happy about that.
Finally, that we agreed that attestation is a fundamental building block.
Yep.
There is no confidential computing without attestation. So the claim I'm making here is that if that is a fundamental property, currently existing solutions do not provide you protection against relay attacks, against diversion attacks, and against replication attacks. These are the three attacks. Pick up any solution of confidential computing. None of that today. Existing solutions, implementations of confidential computing protect you against these three attacks. That's my claim. And I will be happy if you can refute that.
I'm not going to, because it's not a claim I'm making. So I don't. I'm going to close this down now because I don't think this is what this talk should be about. But you're talking about things built on top of confidential computing, yes, using their primitives, but I don't think we can. The claims that I'm making are related to a protocol. They're related to a technology. So I'm going to stop it there. Happy to have the discussion offline. Anyway, thank you everybody very much for your time and for the questions. And if you have any further things, please get in touch with me. Very happy to go into further detail. Thank you.